I noticed I made a mistake right at the end of class on Friday, and it really bugs me. Like if I wrote something wrong on the board, I'm really like anal and perfectionist about that. So I just had to come in and correct myself on this, which was, if you guys remember, at the end of class, I let everyone go like 5 minutes early on Friday, and I was doing a calculation on my calculator on my phone, and I switched a plus with a minus sign. So we calculated that this was about 0.46. And then the number I got for this, it was like 0.5 something. And I was like, well, it's not that great. Like, it's not totally obviously wrong, but it's not super great of an approximation. But that's because I made a mistake on my calculator. So when I double checked the math and I got the minus sign correct, this is also 0.46. So they actually agree to the first 2 decimal places if you can plug them in correctly on your calculator. And don't. I had flipped this minus to a plus sign, which is why it was a little bit off. But it wasn't so off that I realized that I had made a mistake. That's what happens sometimes when you try and like improvise lecture involving complicated arithmetic calculations on a calculator. All right. So let's see. I guess, what else? What is there to discuss? Okay, so I'm going to be releasing some information like about the final and what's going to be going on in the next couple weeks. As usual, I'll put out a list, a study guide for the final. I'll put out some practice problems, which will also count as credit on your homework grade, i.e. extra credit. And then there's also a review session. So, do you guys want a review session? Yes. Okay, I thought so. I thought you'd like that. I'm going to do some review on Friday, but I thought that during finals week, right, like a little bit closer to the actual date of the final, we could have some sort of like informal review where you guys would be welcome to just show up with any questions you might have. I could just have some problems that I could do or like have you guys do as sort of group work or individually. And it'd be kind of laid back. And I asked the department if they would buy us some pizza. They said no. The department said no, but maybe I'll just buy us some or something. I don't know. I'll talk to, I'll see if Maddie wants to help out on that too. So anyway, more info on that to come soon. I'll let you guys know all about that. Oh, and by the way, I don't think you guys know, the final is in a different room. It's in Leaden, I think. So I'll send an email out telling you exactly where the final is supposed to be. Oh, and regarding the review session, so I have to find a room that's available, and I thought I would ask you guys which day would be preferred. So there's not going to be any one day that everyone can make. I apologize for those of you that just can't make it, but I'll try to accommodate the most people as possible. And I was thinking it would be in the evening on finals week, Monday, Tuesday, Wednesday, or Thursday. So for a nighttime, for an evening. Monday, Tuesday. So, here, how about like this? I'm going to find out which people have conflicts. So, among those of you that would be interested in attending a review, so I'm only addressing those of you that are interested in a review. For those of you that are interested, who can not make Monday evening? 1, 2, 3, 4, 5, 6, 7, 8. That's like 15 people. 15, 17 people or so. Who can, for those of you who are interested, who cannot make Tuesday evening? So also about 20 people. For those who are interested, who cannot make Wednesday? It's like 15 people. For those who are interested, who could not make Thursday? It's like 2, 3, 4, 5. It's like 13 people maybe. It's looking.
How about Friday? It's the exam.
Yeah, right, yeah. That would be a lot of math on Friday. All right. Well, could also ask to do it on Sunday, I suppose. Yeah. All right. Well, it's not even totally up to me because I have to ask when the rooms are available. So I'll take this information into account. All right. Any other questions on stuff? Yeah.
Would it be easier to have the review session in the morning?
Okay. Okay, so if there's nothing else, we can start the final section in this class, pretty much what everything's all been building up towards, which is Taylor series. Okay, so I'm just going to start right into it with the proof. It's kind of a proof or a derivation, and it's another one of those sort of iconic proofs or derivations that I remember the first time I saw this. And it's kind of cool. It's kind of neat. So we're going to start off with a kind of zany supposition. Or maybe it's not so crazy, given some of the things that I've taught you guys already. But let's just start off by pretending we have some hopeful, like, fantastical hypothesis that we can take some function, f of x, and we want to write it as a polynomial. So, suppose some function f of x, and let's make this function as nice as it needs to be. And by nice, I mean differentiable. No, I mean continuous. And I also mean differentiable. And I also want the derivative to be continuous. And then I want it to be twice differentiable. So basically as nice as you need it to be. We sometimes call such a function smooth. Which, in other words, means you can take as many derivatives as you want. Most functions we deal with in the class are like this. So, I'll just say having infinitely many derivatives. Okay, so we've got this nice function. And the question is, can I write it as a Taylor series? So here's the hope. That f of x can be written as a Taylor series, which we already know is an expansion in powers of x. Or in other words, an infinite polynomial around, let's say, centered at C. Okay? So we hope that this is possible. We don't actually know. This whole equals sign is kind of, I'm going to put it in quotes because this is a number, this is an infinite series. What does it even really mean for these two things to be equal? But let's just like suspend our disbelief and imagine that this is possible. Then, if if it's possible, check this out. So we're just going to pretend that this is true. Suspend your disbelief, pretend this is true. Then, what happens if you plug in, I'm going to plug in some special points. In fact, there's kind of only one special point to plug in, and that is where the series is centered at, which is C, right? So if I write this out, f of x, it's equal to a0, a1 times x minus c, a2 times x minus c squared, a3 times x minus c to the third, and so forth. So here's the trick, is what happens if I plug in x equal to c? Then I get a whole bunch of terms that just disappear. At x equals c, the left-hand side is f of c. The right-hand side, well, all these terms that have x minus c are gone, right? Because it's c minus c, which is 0. So this one goes, this one goes, this one goes. They all go except for the very first term. OK, great. So we figured out, OK, we got an infinite number of terms here, but at least we figured out one of them, the first one. The first coefficient is just f of c. OK, so that's progress. We still have another infinitely many number of coefficients to calculate. So that was a great trick, but now we've got to do something else. So for those of you that may have seen this, you know what the next trick to do is? Right? So it's like f of x equals a0, a1, x minus c, a2, x minus c squared, a3, x minus c to the third. Anyone know? Well, OK, so we already figured out what a0 is. So I'm kind of not really worried about a0 anymore. And a0 doesn't have any x on it. It's just a constant. So if I take the derivative of both sides, this term drops out. And here, so take derivative of both sides. And on the left-hand side, I'll get f prime of x. On the right-hand side, this term drops out. Here I get a1. Here I'll get 2a2 x minus c. Here I'll get 3a3 x minus c squared. Here I'll just write the next term. It would be 4a sub 4 times x minus c cubed. And now I can do the same trick that I used to figure out what a0 was, which is plug in x equals c. So at x equals c, on the left-hand side, I get f prime of c. And on the right-hand side, once again, all the terms drop out except for the constant one, right? Plugging in c, this one's gone, this one's gone, this one's gone. They're all gone except for that, except for a1. OK, so I'm making progress. I now have what a1 is. It's f prime at c. I'm going to do this one more time, and maybe you'll see the pattern. So now let's take a second derivative. And if I take so I'm now taking the derivative of this whole line. the derivative of the left-hand side is f double prime at x. And on the right, 0, 0, I'll get a 2a2. 0 plus a 0, I'll get a 2a2. I'll get a 2 times 3 times x minus c. Oh, a 2 times 3 times a3, x minus c. I guess all right. I'll get a 3 times 4 times a sub 4, x minus c squared, and so forth. And you guys probably can guess what I'm going to do now. I'll plug in x equals c, and I'll get f double prime of c is, and as before, everything drops out except for this term. Right? So a2 is f double prime at c over 2. Okay, I'm going to put that, I'm keeping track of my coefficients over here, so let's put that here. Do you guys think you have the pattern yet? So I'm going to do, here, maybe this is a little bit of a trick question. Do you think you can guess what A3 should be, sort of based on the pattern? It'll be a third derivative, all evaluated c, divided by 6. Yes, it should be 3 factorial. So 2 is the same as 2 factorial. This is like over 1 factorial. This is like over 0 factorial, which, by the way, 0 factorial is 1. Hopefully you know that. And just, if you didn't believe me, right, like just take the third derivative. F triple prime at x would be 2 times 3 times a3 plus 2 times 3 times 4 times a4, x minus c, dot, dot, dot. So as you can see, 2 times 3 times a3 is f triple prime at c. So in general, our formula for the nth term, it'll be, you guys know what this, when you put an n up here inside parentheses, you guys seen that notation? That means the nth derivative divided by n factorial. So you take n derivatives of f, you plug in c, divide by n factorial, and that's your coefficient. Okay, then let me just rewrite this formula. F of x equal to sum n equals 0 to infinity of the nth derivative of f at c divided by n factorial x minus c to the n. This is the Taylor series for f centered at c. And with regards to this whole issue of, is this equality even valid? Right, like I put quotation marks around equalities because it's always kind of a sticky issue when you're setting some number on the left equal to some infinite series, sum of an infinite number of numbers on the right. And so the rule is we can apply that theorem that we used last time, which says you can differentiate an infinite series. excuse me, you can differentiate a power series as long as you stay within the radius of convergence. So that will be exactly when this holds true. So let me write that. So the theorem is that f of x is equal to its Taylor series where the series converges, i.e., within its radius of convergence. I.e., for x minus c less than r, where this r, of course, is the radius of convergence. In other words, the set of x such that c minus r is less than x is less than c plus r. Right, because we had that theorem last week that said that as long as you stay within the radius of convergence, that's where you're allowed to take derivatives of power series term by term. So it's kind of like, yeah, within that radius of convergence, you can do all the nice things that you hope to be able to do. You can say that the function, the number, the value on the left is equal to the series on the right. The derivative of the function on the left is equal to the term-by-term derivative of the series on the right. So it's kind of just what we would hope for. All you got to do is just make sure you stay within that radius of convergence, right? It's nonsense once you get outside the radius of convergence. So a lot of times you'll have a series and like your job will be to figure out what the radius of convergence is. Now, back when I did power series, I did them in general centered at a point C, but I said usually just C is 0. So that's also the case with power series, with Taylor series. Usually they're centered at 0. It's kind of the most convenient and obvious and useful choice. There's a special name. So when C is 0, which is usually the case, we call this a Maclaurin series. I.e., f of x equal to its Maclaurin series is the sum from n equals 0 to infinity of the nth derivative of f, but now c is 0, so it's evaluated at 0 divided by n factorial and just times x to the n. So that's the Maclaurin series. Okay. So, all right, now you've seen Taylor series. Yeah, that's what you've been waiting for all this time. It's super useful, man. Like I remember I was taking a physics class at UCLA. Well, I couldn't decide between math and physics. I thought they were both so cool, so I tried to do them both. Eventually, I'd taken so many classes that UCLA told me, all right, Mr. Ciotti, pick one and graduate already. And I was a bit closer to a math degree than a physics degree. I really hated those physics labs, too. So I put those off. And it was a good, so I never did take them because I just took my math degree and graduated. But in the physics classes that I did take, I remember, I had this one really cool TA. I always remember him. I really knew what he was talking about. And one of the first things that he told me was that physics is all Taylor series. And I barely even knew what Taylor series were at that point, but I was like, maybe I should pay attention to these things. And sure enough, he was right. I did end up using them over and over and over again, which I expect you guys will too in engineering. So let's do some examples, some common popular examples with Taylor series. So some of the most useful, important functions we deal with in this class are here's some important functions. Well, e to the x is a big one, ln x is a big one, and then sine x and cosine x. These are all sort of really fundamental to this class. So why don't we start off with some of these? Let's see, e to the x, that's an easy one actually. Let's start with that one first. So let's do the Maclaurin series, which i.e. Taylor series centered at 0. For e to the x. So we are going to write e to the x as the sum of, okay, here, well, first let me just notationally, so let's let f of x equal e to the x. Man, what smells so good in here? Just put on perfume or step out of the shower or something? Is it just me? Am I smelling things? Okay. So let's use that formula over there. E to the x, we need its nth derivative at 0 divided by n factorial times x to the n. But e to the x is such an awesome function because its derivatives are all itself, right? F of x is e to the x. F prime of x, that's also e to the x. The nth derivative of x is also e to the x. So when we evaluate it at 0, it's all just 1, right? F of 0 is 1. F prime of 0 is 1. The nth derivative at 0 is 1. So all these coefficients are all just 1. So this is equal to 1 over n factorial times x to the n. So that's equal to 1 plus x squared over 2, x to the third over 3 factorial, and so forth. Which you might recognize, I actually did this last week, and I told you it was going to be e to the x, and I told you that I would eventually prove to you that it was e to the x, so I have now proven it to you. Or have I? So I haven't talked about the radius of convergence yet. This might not be true. It'll be true if we're within the radius of convergence of that series. Now, we actually already did calculate the radius of convergence of this series last week. Does anyone remember what it was? See how photographic your guys' memories are.
Didn't you say that it's everywhere?
It is, yeah. It's infinite. Right. Oh, nice one, Robert. Yeah, okay. So yes, this has an infinite radius of convergence. If you're not sure, if you don't remember how we got that, we used, as usual, the ratio test. So I encourage you to check that for yourself. We'll do more examples today, but we showed last week via the ratio test that this series converges everywhere. i.e. The radius r is infinity. So this is actually true everywhere. Kind of tempted to like plug some numbers in just to, you know, how well that went last time. All right, I want to try. Let's just plug in like a nice easy number. How about 1? So e to the 1 is e, which is okay. I know the first 2 digits. It's like a 2 and a 7. Maybe a 1 after that? Okay. So is this, I'm kind of curious, like how close that is to 1 plus 1 plus 1 squared over 2. Well, that's 2.5. Okay, let's go one term farther. Plus 1 to the 3rd over 6. So this is about 0.15, I think, 0.17. Here, so this is like 2.5 plus a 6th, which is like 2.67 or something. What's 1? Oh yeah, 1/6 is half of 1. Yeah, 0.16, 0.17. Yeah, okay, yeah, okay. So as you can see, going out to the 3rd degree term, we got 2.67 compared to 2.78. So it's pretty good. Yeah, not bad at all. Okay. So next, that's e to the x. It converges everywhere. If you might notice, like I did this approximation here, and I only went out to 3 terms. Obviously, like the more terms you go out, the closer the approximation is going to be, and you can pretty much get as close of an approximation as you want, depending on how many terms you go out. That's the sort of question a numerical analyst would be asking, like what sort of error do I get on this approximation? Now, I have never taken an applied math class in my life. I don't intend to, although funnily enough, I'm actually doing applied math, which is fluid mechanics right now. But if you do go into that sort of thing, then you will be asking yourself the question, like, how many terms in this series do I need to go out to get within, 1% error of the actual value? I think that stuff's kind of dry, and I don't like to get my hands dirty with actual numbers, so maybe I'll leave that for you guys to suffer through once you have to take numerical analysis or something like that. Or we might do a little bit of it in this class, but here, I've got some other. You know what I'm going to do today is I'm going to do the series for e to the x, and then I'm going to do sine x, and then I'm going to do a trick to get cosine x, and then I'm going to prove Euler's formula, which I promised like a month and a half ago, back when we were doing imaginary numbers. And I said that maybe we'll prove it at the end of this class using Taylor's series. So that's what I'm going to do. So now let's do sine. So let's, just for notation, let me set f of x equal to sine of x. Here, so f of x is sine x. I'm going to take some derivatives. F prime is cos x. F double prime is negative sine x. F triple prime is negative cos x. The 4th derivative is back to sine x. The 5th derivative will be cosine x. It starts repeating after you take 4 of them. So now let me plug it in at x equal to 0. So f of x sine x. So now Here, this will be the at x equals 0 column. So sine of 0 is 0. Cos of 0 is 1. Sine of 0 is 0. Negative cos of 0 is negative 1. Sine of 0 is 0. Cos is 1. It just goes 0, 1, 0, negative 1. 0, 1, 0, negative 1. So in general, the nth derivative of sine evaluated at 0, it is, well, it's 0 for all the even ones. And then it's either 1 or negative 1 for the odd ones. Here, so I'll say it's 1 if n is 1 more than a multiple of 4. And it's negative 1 if n is 3 more than a multiple of 4. Right? That's just a way to number the series that goes 0, 1, 0, negative 1, 0, 1, 0, negative 1. Here, I'll simplify up the notation in a second. Let me just write out the series, and then you'll see. So if we plug in the nth derivative at 0 over n factorial times x to the n, it'll be, okay, there's no constant term, but then we get an x. There's no second degree term, but then we get a third degree. All right, now I'm on this one. No fourth degree, but then we get a fifth degree term. No sixth degree, but then we get a seventh degree term. Okay. You guys all right with that? Anyone want to stop me and ask a question at this part?
Yeah, how would you see that?
These ones?
Well, repeat what you just said about that was.
So, I mean, here, I can write it like this. It's f of 0. Then we got f prime at 0 over 1 times x. F double prime at 0 over 2 factorial times x squared. F triple prime at 0 over 3 factorial times x cubed. And then we already calculated there, this is 0, right? This number is 1, so that gave us this term. This number is 0. This number is negative 1, so that gives us this term.
That's good. Thank you.
Thanks. You're welcome. All right, so we've got the series for sine. A couple things I want to point out, which maybe aren't that surprising. Notice the only powers of x that are present here are odd powers. And that should make you think, well, sine is an odd function, right? This is y equals sine, right? It's odd, meaning f of negative x is negative f of x. So once again, the sort of connection between the word odd and odd powers. Odd functions only have odd powers. This is actually true of the Maclaurin series for any odd function. But so anyway, yeah. So that's not surprising. Okay. In fact, here you might as well save this formula, like put it on your cheat sheet or in your notes, and same with e to the x too, because these are all super important. And now let's get cosine, but I'm going to do it in a different way. Here, let me just call it, well, let's cos x. Okay, now for cosine of x. Oh, crap, I'm getting ahead of myself. There's one more thing. Yeah, I still need to talk about one more thing for sine, which is where does it converge, right? Like where is this equal? Any guesses based on the coefficients? Because we've got factorials, and factorials like get really big, but they're in the denominator. So this is looking like one of those ones that's just going to converge everywhere again. So here, let me write this out in a more compact form. So this is the sum from 0 to infinity of, okay, it's going to be, if this is the first term, second term, third term, x, or no, let's say this is the 0th term, right? If like n is 0, here, let me use k, because this is not the same n as that. Here. So here, check. I claim that this is true. Why don't you check this? This is just like a more compact way of writing this. Right, like if we check, if you plug in k equals 0, we get x. If k is 1, we get minus x cubed over 3 factorial, and so forth. Okay, so hopefully you guys believe this formula. The reason I wrote it like this was because let's check what the radius of convergence is. So here, let's call this, say, Bn, and let's do the ratio test by taking the ratio of 2 of these consecutive terms. Right, so that'll be, okay, this is going to get a little bit messy. -1, sorry, not Bn, Bk, my bad. I'm using k as my index. Bk, let's call it k. Okay, so this will be -1 to the k plus 1. Let's see, we get to cancel the negatives. Those don't matter. We get to cancel all but 2 of the x's. Right? These all cancel with that. So there's still x squared. And we get to cancel most of the factorials. Right? I get this is 2k plus 3. So I can cancel this with all but, I'll get a 2k plus 3 and a 2k plus 1. Well, what does this go to when k goes to infinity? It goes to 0, yeah. Just kind of like what we suspected. This was kind of a long, messy way of having to prove it. But anyway, the point is, so this series converges everywhere. Just like the one for e to the x. Okay. Yeah, that's kind of a messy calculation, but all right. I just had to check that so that now I know if I'm allowed to take, okay, well, to do the next trick that I wanted to do, which was get cosine, but in kind of a sneaky way. Okay, so now let's get the series for cosine x, but I don't want to have to go through all of this like rigmarole. Rigmarole? I think that's the word. Like I did all this work. Is there a shortcut? Is there maybe some other relationship between sine and cosine that I could exploit here? What's the calculus relationship between sine and cosine? That the derivative of sine is cosine. And, okay, well, we've got the series for sine. And we already know it converges everywhere. So I can use the theorem that says I can differentiate term by term on this guy. Here, let me just leave this up, actually. So if I differentiate term by term, this expression, on the left-hand side, I just get cosine of x, right? Because that's the derivative of sine. On the right-hand side, well, let's start taking derivatives. Derivative of x is 1. Here, I'll get times 3, right? Like what's d dx of negative x cubed over 3 factorial will be a minus x squared over 2 factorial, because the 3 and cancels with that 3. What do you guys think the next term should be? X to the 4th over 4 factorial, which is exactly the derivative of this term, because the 5 cancels with that 5. And then minus x to the 6 over 6 factorial, and so forth. So there is your cosine series. And let's see, sure enough, it only has even powers, kind of like what we would expect. It's like I'm not going to have time to prove that Euler formula right now. Yeah, there's a few things I wanted to do, but I'm not going to have time to do any of them in 1 minute. Hey, this speaker's been on this whole time, hasn't it? I usually turn it off. Yeah, I guess I'm just going to stop here for now, and I'll pick up on this on Wednesday.